Hello, everyone. Thank you for joining this seminar series organized by the Empathic Computing Laboratory. I'm your host, Aladdin, and our guest speaker for today is Thijs Roumen, who is an assistant professor at Cornell Tech in New York. His research interests are in digital fabrication and HCI, and has done a lot of research since 2015 or 13, I'm not sure, but the title of the talk is Portable Laser Cutting, and the talk will be roughly an hour, followed by a brief questions and answers. Thank you all for joining us. Welcome, Thijs.
Thank you for the introduction, and welcome to my talk on portable laser cutting, which is work that I've largely done in collaboration as part of my PhD with Professor Patrick Bowdish at the Hasselplattner Institute. Let's see. So when I started to do research in laser cut models essentially look like this. It's a vector file that as the laser is going to traverse these red outlines here of the plates so that it kind of cuts individual plates out of a sheet of material, which creates individual pieces which you can then assemble into a 3D model by kind of putting these pieces inside each other. And just by looking at this particular cutting plan, you get a pretty reasonable idea of what is going to look like, right? It's not some sort of machine format that you're staring at here. It's actually pretty reasonably well understood what is going to happen. So there's a lot of great things about this particular cutting plan, but today I'm here to tell you that this format will have to go away, and we'll have to start thinking in a completely different way about what models for laser cutting will look like. Before I'm going to go in more detail on that, let's zoom out a little bit and look at where laser cutting comes from in the first place. So laser cutters have been around since the 60s, and they're a really fast and precise fabrication machine. So here's an example of a laser cutter which is cutting individual pieces out of a plate of a sheet of wood material in this case. And you see that in a pretty high speed, it actually kind of managed to cut these individual pieces that you can now kind of put together, assemble into a 3D model. And that allows you in this case to make the neck of a guitar that we've been cutting. And I'll show you more of that later. But as I said, laser cutters have been around since the 60s, but initially only or primarily in an industrial context. And this has been like that until about the 2000s, when the first patents of the initial technology started to expire and the technology became much more accessible to a much broader range of users. We call these the people who start to kind of adopt technology early on tech enthusiasts. And I am really curious about what the next big transition is. So this is sort of the phase where we are right now, right? We've had these tech enthusiasts kind of pick up laser cutting, and I'm really excited to kind of find out what the next big pivotal moment in the timeline looks like. So what it takes to kind of make laser cutting relevant for the other 99% of people in the world. My working hypothesis as part of my PhD is that this has to do with portability. And portability in the context of laser cutting is the ability to reproduce models independent of the laser cutter, which would then allow users to reuse and advance models by building on the work of others and increase the complexity of the content that they can make. So before I'm going to kind of go in more detail about what portability looks like in the context of laser cutting, let's look at a field that we're all much more familiar with, which is the field of computing. So in computing, if you look at the timeline of sort of the period from the first piece of hardware in computing towards the adoption of personal computing as sort of a more widespread kind of phenomenon of computing that was accepted, we've seen sort of the number of programs that have been written in the process kind of increase exponentially over time. Initially, there was a long period where programs are written for very expensive hardware, right? So you would write your code so that it would run on one specific piece of hardware. And then whenever you would change the hardware, you would have to throw away the code, start over again, and kind of adopt to the new context. And then later in that timeline, there's this period where programs were written for multiple platforms, right? This code is much more flexible and could be kind of reused across many more users and across many different platforms over time. So the key question for me is what happened in between, right? How did we go from this sort of very handwritten assembler code approach towards these high-level programming languages that we are seeing right now? And the answer to that is it's not been one pivotal moment, right? There has been a period in which that change has sort of manifested itself. Initially, the first kind of person to kind of investigate this was Corrado Bohm in 1951, who kind of wrote the first sort of theoretical concept of what a compiler could look like in his PhD thesis. A year later, Grace Hopper actually implemented the first practical compiler, which you would today more look at as if it's a linker, so for her A0 programming language in 1952. About a decade later, actually, the first cross-platform compiler was implemented. So like in the COBOL programming language, there was a piece of code that would actually execute on the UNIVAC 2 architecture as well as the RCA 501 architecture. And you would expect it by now, like people are extremely excited about like the idea of like portability and compilers. But it turned out it was not so much the case. And the main reason for that was that like the software was like much more flexible at this point, but it was still kind of would be vastly underperforming compared to the software that was written specifically for the hardware that was targeted. So it was not very performant. It was only sort of a decade later where the first sort of portable C compiler was developed that compilers and the idea of portability kind of became a big deal. With the portable C compiler, entire operating systems were written in higher level programming languages, and you know, like everything that we have written since then, or what most of us have written in as part of our research, is like a much higher level than actual assembler code on the hardware level itself. So each of these steps in this timeline, I think, is an increase of portability, right? Like we've kind of traversing the field upwards in increasing degrees of portability, writing software that is more accessible, kind of easier to share and build on the work of others. So portability in the context of computing is the ability of software to be transferred from one machine or system to another. And we tend to capture that in the form of standards, right? And the standard is an established norm or requirement for a repeatable technical task. And if we look at sort of like the bigger picture of like how that has impacted the world, we've seen sort of like in the context of computing, the hardware being introduced in the 40s, the first compilers being written in the 50s, and then in the decades afterwards, sort of that idea getting adopted and turning it into a mainstream phenomenon. But we see the same thing in other forms of digital content. So like in desktop publishing, the first laser printer was built in the 60s, and then like in the 80s, Adobe came around with PostScript, and later with PDF as sort of like a portable standard that would be used across the entire spectrum of the field. And the models that are like the models in this case, the documents that are written since then can still be opened and used today on today's hardware. And the same thing with digital video, digital audio. Essentially, any form of digital content has gone through this transition from being very hardware specific and being very hard to modify towards something that becomes much more portable and it's standardized and then kind of allowed for mainstream adoption across the board. So on a more abstract level, portability is the ability of something to be transferred from one machine or system to another. And now I have a definition that I can actually apply to the context of laser cutting, right? So in the context of laser cutting, it would be the ability of models to be transferred from one machine or system to another. So let's look at what is preventing portability in laser cutting right now in the current state. So I've shown you this cutting plan of this thing here wants to become a microscope, right? Like, so it consists of a whole bunch of plates that are all kind of assembled in 3D into that microscope. And you know, there's many good things to be said about this 2D cutting plan already, right? It already is like reasonably portable, or at least it came a long way. Back in the 60s, the first laser cutters kind of operated using custom electronics that would then drive the individual motors and specific drivers for the optics, right? So like everything was like sort of optimized for one particular machine and would run only in that one lab context in which that laser cutter was being used. It was then in the 80s that G-code was adopted as sort of the standardized interface, which was already invented in the 50s, but only became sort of adopted in the context of laser cutting in the 80s, because this was the moment that multiple people started to use the same laser cutter for different purposes. So there was a need for sharing content and kind of building on the content that was out there. And it was only in the 2000s that like sort of the line drawing SVGs were kind of adopted as the standard. And they are then under the hood converted to G-code by a driver, right? So like under the hood, it still kind of operates in the same way as in the 80s. But there's also many limitations to these 2D cutting plans. Let's look back at that microscope that I've shown you before. You can imagine that if the laser is going to traverse these individual lines, it's going to remove an amount of material, which is something known as curve, is the amount of material that is being removed by the cutting process. And so when you're trying to assemble this model, for example, you want to put this piece here inside this cutout, you can imagine if the laser removes more material than the original design, in some ways these red lines, they become a little bit thicker, right? And what this does is that it makes this prong here smaller, while it makes this cutout wider. And so these pieces will not fit with respect to each other, right? You try to assemble them and they just fall apart right away. The same thing happens in the opposite direction, right? If my laser removes less material than the original laser cut model, then the prong gets too wide, it gets wider, and the cutout gets narrower. So again, like you might want to push them together, but they will not fit. They're like misdimensioned. This is a concept known as curve, and this is like a problem that is like embedded in all of the sort of like laser cut piece that you have here. And not only does it cause problems here when two laser cut parts touch, but it also creates problems when, for example, here a bearing needs to hold an axle in place, right? You can imagine the same types of problems. Like if the bearing gets too wide, the axle gets wobbly, and if the bearing gets too narrow, the axle will jam in place and it will not move. So if only we were able to handle these two kind of special cases where like kind of curve makes it impossible for this model to work, we would have something that's actually good enough to be able to reproduce. So I would have a model that I can reliably send over to somebody else and they would be able to reproduce the very same content. But there is an even nastier situation here. Like, as I said before, this thing wants to become a microscope. So what if I want to change, for example, the length of the neck of that model? Now, I can obviously do that in 2D, right? I can change this individual plate here. But you can imagine that there is like more change that needs to be made at different locations in that cutting plan based on how the plates are connected to each other. So that this actually becomes like a consistent 3D manipulation. So being able to edit these models would be yet another level of like abstraction that would be even more powerful because it would allow us to do so many more things. So let's look at the research that I've been doing in order to kind of address these type of problems. In the scope of my PhD, I've been publishing these 15 papers at Chi and WIST. And in the interest of time for this talk, I'm going to focus on the big ones that you see here on the right. So the first thing I wanted to do as I was like sort of encountering this problem was trying to see if there is a way to kind of create a minimally invasive approach. Because as I said, the 2D cutting plans are very beautiful. They have a lot of great properties. Can I find a way to save them? You know, kind of stick around with the original 2D cutting plans and just make them a little bit better so that all the problems that I'm looking at are resolved. This is a concept I refer to as low-level portability. In order to do this, I wrote a semi-automatic tool to convert machine-specific cutting plans to machine-independent cutting plans. And there are two publications that are sort of associated with this work. And the goal of this software is to take this microscope here, which fabricates only on one particular laser cutter and in one specific material, and translate that into this microscope, which actually fabricates on a range of laser cutters, at least on all consumer level laser cutters, and in a range of different materials. And the way it achieves that is by adding these additional incisions in the cutting plan, right? So like you see here, like where there were the initial sort of joints, SpringFit has made these joints portable. And it did that by increasing the tolerance of the joint. So if you look at the joint here and in close-up from the side, you see that there is like the joint itself, and then there is like this sort of cantilever structure that is sitting right next to that. And that actually kind of, as you press the material together, is much more tolerant to variations than the original material it was itself, right? The material itself was very rigid, and now it's much more flexible, allowing for a much broader range of like tolerances of laser cutting to kind of work out the same model. The other thing is like there are these moving parts in this model, right? So like as I said before, like where a bearing needs to hold an axle in place. There's another piece of software that is like sort of related to this, which is called Curve Canceller, which we wrote in order to kind of make these moving parts portable as well. So the way we did that is like we add this additional incision right next to the cutout. So like here is the dashed outline here is an axle, which is jammed inside the bearing. And there's an incision that sits right next to it, which is this crescent-shaped kind of cutout. And as curve is applied to this mechanism, you can imagine that like all the lines get a little bit wider, right? So like the crescent-shaped inset gets smaller, and it does jam inside its own cutout. So like there's always a way as it jams sort of itself inside its own cutout, where it closes down the gap that is caused by curve exactly. You see here with simulated amounts of curve, right? So here's the same mechanism fabricated on different laser cutters and even fabricated on a milling machine. And you see like sort of the mechanism, even though the curve went up by an order of magnitude, the mechanism still holds the axle in place well. A curve canceller and SpringFit, they come together in a software tool that is like a browser-based application that is like running TypeScript, and it directly takes the SVG cutting plan, which is an XML format under the hood, and displays that, and then allows users to kind of come in and modify the model so that it actually becomes a portable model that we need it to be. The first thing is it automatically identifies where possible joints and mechanisms are. You see that here highlighted in these colorful shapes. And then a user can come in to still make additional adjustments because, for example, this rectangular cutout you see here is just a rectangle in the cutting plan, but it actually wants to be a sliding mechanism. So as a user, you can now come in and you can add these additional sort of annotations into the mechanisms to enrich them with the information needed to kind of make this model portable. You see here, user do here with like that sliding mechanism. And similarly, there are some of the guesses of the system that may have been wrong. So for example, this thing here on the top here is like identified as a bearing, but it really is just a thing that holds the Petri dish in place. So a user can come in and kind of override the suggestions from the system to then create the microscope that you want it to be. And because it's already in the browser as an SVG file, you can immediately save it and send it off to your laser cutter to now fabricate that microscope that works independent of the machine that you're using and on a range of materials. You see here demonstrated. Even when the same mechanism is actually fabricated using a milling machine, which removes much more material. And so we've used a combination of spring fit and curve canceller to convert a range of models that we found in online repositories. And here you see like every time like the origin, like a version of the wooden model, as well as like sort of the same thing fabricated using a completely different material or using a different laser cutter to kind of confirm that it still continues to work reliably. So how well did I do so far, right? I mean, at the beginning of this talk, I promised you portability. And, you know, I think the resulting models, they now cut on any laser cutter or any consumer laser cutter at least. So, you know, we've achieved some form of portability here. But it also came at a cost, right? Like I can't help but look at this model and realize that there is like a certain aesthetic as well as a structural cost that comes by adding all these additional incisions in the joints here. And there was actually a bigger promise I made you at the beginning of this talk, right? I promised you that we would be able to edit these models. Adding all these additional incisions into the cutting plan actually makes that even harder, right? Like now there's even more stuff that needs to move correctly with respect to each other. So while this is a great approach to kind of make models easily kind of reproducible, and you can just send it over to somebody else and you know that the model will work after it's been modified with curve canceller and spring fit, modifying these models and making high-level parametric changes is still a hard process to do. So let's look at a completely different approach to kind of to solve this particular problem. Here is a model of a VR headset, and you're probably all familiar with this thing. So it's like based on Google Cardboard. You put the phone in the back of the device, and then there's like two lenses that you're looking through to give you a reasonable VR experience, which then displays different content for your left and your right eye to kind of create this sort of like VR experience that you might want to have. But this model is not particularly inclusive, right? If you think about this particular model, it's optimized for one particular user. And so like, for example, like the interocular distance is a fixed distance at this point. The distance between the phone and your eyes is a fixed position, which I probably want to change because of my prescription, right? I want it to go a little bit further away so that I can focus on the content. And the shape of your head is, of course, also like a big factor in the particular design that you see here. So there's all these kind of changes that you might want to make to this particular VR headset out here. And in a 3D modeling environment, this would be trivial, right? In a 3D modeling environment, you would do something like this, like you take like a stretch tool and you take the backplate of that model and you just sort of drag it so that it becomes longer. But this model is not shared in the form of a 3D cutting plan, right? This model is shared in the form of a 2D cutting plan. And in 2D, that modification is much, much less trivial to make. I would obviously have to kind of change the plate on top that I was looking at, right? Like that, if I modify it, if I want to make it longer, I have to stretch that plate. But when I do so, I also need to change the plate that sits right next to it, right? Because the joints have changed now. And so in order to kind of make a consistent modification, I have to change both of these plates. And I'm going to need some of your help here. So I'm going to go through the individual plates. And if you think that I need to change one of these plates in order to kind of stretch the VR headset longer, you just like raise your virtual hand, or if you have your camera on, you can raise your physical hand. So who thinks that these have to change? Not so much. What about this plate here? I see like a hand coming up. That's right. So like this is sort of the bottom plate of that VR headset, right? Like if I only stretch the top plate, I would sort of skew the model. I don't want that. So like I also stretch the bottom plate so that it's a nice straight extrusion of the overall model. So yeah, I agree. I would also change this plate. What about this plate here?
I'm not sure.
So,
I'm trying to see your cursor. Is it?
oh no, like you don't need to look at my cursor. Like it says like the highlighted plate here.
Oh, okay.
It looks like the same one. Are you
So-
changing the slides? Are you changing the slides, or it looks like the same plate as last time?
It looks like this. It looks like this plate, right? This one on the side here. Are you seeing the same thing as what I'm seeing? Is the bottom right plate that is now highlighted?
I think, yeah, now I think the slides are catching up. So we see the bottom
I
right.
see.
Yes, yes.
That
Sorry.
explains. All right. No worries. So yeah, I would also change this plate, because like if I have like only one side plate, I need to modify both side plates again for like creating a nice straight extrusion. So what about, yeah, no, I don't know who sees what. So this is the plate that holds the lenses in place. You would not have to modify that one. Same with the back plate here that sits at the back of the device. And then there is this plate here in the middle that sort of sits on top of your nose. If anyone thinks that we should change that one, maybe not. So this plate, actually, this was an interesting sort of thing. Like actually, when we submitted the paper, I think we said that you did not have to change that plate, because there are no joints that are connected to that particular plate that are modified at this point. However, in order to kind of optically fix the model, like you don't want to see with your left eye the content of the right side and the right eye the content of the left side. So you kind of do want to stretch this plate longer. So in the final submission of the paper, we actually changed that and we fixed that error ourselves. But just the fact that there was discussion within our team was already kind of an interesting observation here. I think as you were going through this exercise, what you really have been doing is you've been imagining what the model looks like in 3D and what the modification is that you have to make in 3D to then kind of figure out how to kind of translate that to the individual plates. And of course, I primed you a little bit by showing the 3D model before. So I can't help but wonder what it would have been like had I had this model in 3D in the first place, right? It would be much easier. So while I did the work that I've done that I've presented so far, at the same time, we in the larger team at the lab start to develop a 3D modeling environment for laser cutting. It's called Cube. And here you get a bit of a preview of like a sense of what it looks like. So Cube is essentially sort of a Minecraft style interaction where you kind of click together a bunch of boxes. And then you can make stretch operations and all kinds of other operations to go off the grid and kind of make more complex modifications to your model. You can add these roundings. You can even stretch those to kind of make them exactly the way you want them to be. Add cutouts, add engravings. And so in a couple of minutes, I mean, this is sped up, but like in reality, this would have taken me 4 minutes to kind of model this thing. I could in 4 minutes create like a reasonably complex like mock-up of an espresso machine that you see here, which is nice, right? Like, I mean, it would have taken me probably a day to do in 2D, because you have to kind of create all these joints and figure out how everything lines up and it's connected to each other. So this is a great step forwards in terms of user interface, but it's also a huge step forwards in terms of portability. Because right now I can export this model. Once I'm done modeling in 3D, I can export that model and configure the settings of my particular machine and my particular material. So I create a cutting plan that's optimized for my use case, as opposed to sort of like a cutting plan that only works on one machine and one material. And of course, not everybody knows the properties of their machine, let alone like the properties of the machine in combination with material. So if you don't know that, you can kind of create one of these test strips to kind of measure the curve on your machine and then adjust the cutting plan accordingly. And so right now we have like about 600 beta testers in Cube that are like creating all these new types of models and this content. And these models are all inherently parametric, right? Like you can make all these volumetric changes and these parametric modifications essentially for free, because these models are already out there. And you can continue to build on the work of others by taking one of their models and kind of adding additional content to them. Actually, right now we're in the process of turning Cube into a real startup. So like this has been going on for a while at the lab. And again, like I've been involved in the research part of this, but there's a bigger endeavor of like turning this into a real company at the moment, which happens to be also led by my wife. So like it's also moving along with me to New York City. which is really cool because like we're using this software right now to kind of run a series of workshops, so that at different schools, so kind of have school children kind of learn how to model for laser cutting, and then create their own musical instruments, Bluetooth speakers, furniture, all these sort of pretty advanced sort of structures that were very, very hard to kind of model before. And you see some pictures of like children getting very excited about it. And it's not just exciting because they can now make all these things, but they can also use it for other kind of objectives within their curriculum, right? So the music teacher gets equally excited about this because now they can learn how to play these instruments as well, and kind of learn about like the physics of the instruments to kind of like connect it to the other parts of their curriculum. On the most extreme example of that is something that we've recently succeeded at is cutting a fully functional laser cut guitar based on the software that I've just shown you. And so this is something that is currently in submission to the Symposium on Computational Fabrication. So I hope by Friday to have more good news that you will actually be able to read the paper about this and be excited about the actual result. So it's a little bit like secret still. All right, to come back to the main story, with Cube, in many ways, we're done, right? I've shown you like 3 types of issues in these cutting plans, and they all work great now, and everyone can edit and build on the work of others. But I don't know how you guys feel about this. But if I come around and I just like tell everybody that they should stop doing what they're doing and use a completely different paradigm of modeling their content, it's probably not going to happen overnight. There's a lot of really great models out there that are encoded in the form of 2D cutting plans. Right? There's entire engineering careers and design careers that are hinging around creating these really advanced laser cut models that are being shared online right now. And I think as long as that's the case, these 2D cutting plans will continue to remain the standard. And the thing with standards is they tend to stick. So I don't know if any of you play guitar, but like when I was born, guitar tabs were shared in sort of this ASCII format that you see here, which, you know, it's just good enough to sort of share all the information you need to be able to play this particular riff you see here. But I'm sure anyone in this talk can also think of like, you know, a more elegant, easier to edit, easier to share type of format to kind of represent the information that is embedded in this particular riff you see here. The sad thing is, this is something I've actually downloaded a couple of months ago from a sharing website, right? So there's like, since I was born until now, there's been not really any change in the way we're sharing these models. And the reason for that is it works just fine, right? It's just enough information to kind of make it work. And I'm afraid as long as that's the case for these guitar tabs, the same is going to hold for laser cutting. So that modification to that VR headset that I showed you before is not going to look like this, but it will continue to look like this. So to find out how bad this really is, we ran a study in the lab, and we had like 13 participants try to reproduce the workflow that you just tried to reproduce as we were talking over it. And this took on average 24 minutes for our participants, and 11 out of 13 models failed when we tried to fabricate them. So if users have to mentally reconstruct a 3D model from these individual 2D plates, why don't we go for 3D right away? Why don't we write them software that makes them really good at this? This is where Assembler Cube comes in. So there already is software that takes 3D models and then convert it down to 2D cutting plans like Cube and FlatFab, but there's no software that goes the other way around, right? It takes a 2D cutting plan and then kind of promotes it to a 3D model. It also feels a little bit like a workaround, right? Like you take a 2D cutting plan, you turn it into 3D, you make a modification in 3D, and then you export it down to 2D. But this additional workflow turned out to be 10 times faster than the original workflow, and all models continue to work as a result. So let's look at what Assembler Cube really is. Here you see a user using Assembler Cube, and you see that they're essentially just sort of puzzling together that VR headset from its individual plates in the 3D editor. That's all good and well, but of course, in order to kind of be able to do this, there's a long sort of pre-processing pipeline that actually allowed us to kind of do this. Like, you know, you all kind of get suspicious when I show one of these videos because you know that there's much more going on here than just the user clicking together individual plates. So let's look at what is happening under the hood here. Assembler Cube really is a 5-step algorithm that converts 2D cutting plans into 3D models. Let's look at the individual steps. So the first step, Assembler Cube tries to kind of identify what are plates and what are cutouts in the model. And it does so by alternatingly assigning plate versus cutout to the individual cutting lines that the laser traverses as it cuts the pieces. Then it uses that information to kind of look at the outlines of these plates and detect individual patterns, like recurring patterns of structures, which could well lead to like kind of identify individual joints on the model. It uses that information then to kind of derive the material thickness of the model by a simple voting mechanism where we just like let all the joints vote for what they assume is the right material thickness. And then a majority vote allows us to kind of identify the actual material thickness of the model. Then it tries to pair up these individual joints. And finally, in the last step, it uses semi-automatically assembles the model into the 3D model that you see before. And that's the workflow I just showed you. In the interest of time for this talk, I'm going to focus on the last 2 steps of the algorithm in more detail. So here is the VR headset, the cutting plane of the VR headset again. And the algorithm already succeeded at like finding out where the plates and the cutouts are in the model. You see that by the gray highlighting. It also identified the individual joints and the material thickness. And now it tries to pair up these individual joints. So before I'm going to show you like how the algorithm does it, let's try to do this ourselves in our head. So I'm going to need some of your help for this one again, and I hope that the slides catch up so substantially this time. So I want to find out what this plate is connecting to. And this plate is sort of the back plate of the VR headset. And I'm going to go through the individual plates to kind of, and you raise your hand or your virtual hand if you think that I need to, that they are connected there. So who thinks it's connected to this plate here? Not so much. This plate. This plate is indeed like, so I see a lot of hands going up, right? So this is the bottom of the VR headset. So like the joint you see here in the bottom can be connected to kind of one of those types of joints you see over here. And what about this plate? So yeah, I see the same sort of hands going up. So this is the same problem, right? Like, so this is the top of the VR headset. And so like this joint here can be connected to that individual joint here. So, you know, as you guys were going through this exercise, you've actually probably been comparing this joint to like similar looking joints, right? Like you've not compared it to this little feature here, which is also a joint, because you just know that it's never going to fit, right? It's like your intuition tells you that this is not going to be a matching pair. Algorithmically, it's not that trivial though, right? Like algorithmically, you would have to compare every joint to every other joint in the model and each step in the algorithm, which would lead to at best quadratic complexity for every step of the algorithm. What we try to kind of capture that notion that you had, this intuition where you kind of try to compare joints to kind of like by a global structure in the form of a hash data structure in our algorithm. So by looking at the shape of the joint and hashing that, like creating a key for looking that up, we actually had a signature for each joint. And then we only need to look at joints that are like have this share the same signature. So like the search space is reduced dramatically. Let's look at how we really do that. So here's one of those joints, and like let's zoom into this joint. And so the key thing to kind of make this lookup table work is like to find out what the key for the hash really is, right? So our initial intuition was to kind of use the size of the finger as the key for the hash data structure. So like if you would find other fingers that match the cutouts that match this finger, we would be good. The problem though is that this finger wants to mate with a slightly smaller female feature. And the reason for that is obviously curve, right? Like the model has been adjusted so that it fits, that it can actually be fabricated on a laser cutter. Because somebody has made the fingers a little bit bigger than the cutouts that they need to fit in because material will be removed. So that's not great because like if a feature is slightly smaller than the initial, we will not find any matches in our hash data structure, right? We can only rely on perfect precision. Otherwise, we will not get any results. The good news is that the feature that sits right next to this finger is a cutout from which the same amount of material has been removed to adjust for curve. So if we add these two features as like one individual signature for like this particular joint, we actually have a signature that is robust to variations in curve. And that now allows me to kind of find these individual matches in the model. So if I now look up this green joint in my hash data structure, I find these orange joints as like sort of the collisions in the hash. So these are like the things that share the same signature. And I can use that to then identify what are the potential candidates to pair this joint with. So rather than comparing to all the other joints, I only need to compare 8 joints, K joints at this point, which narrows down the search space dramatically. But there's still K joints. right? If it was one joint, I would be done. Like I would know exactly which joint goes where, like everything would be solved. I would have a 3D model. But there are still K of them. And this is where we bring in the user to kind of do this last step of disambiguation. And this is what the workflow you saw before, right? So user loads the 2D cutting plan into the editor. And then uses this assemble tool to start assembling the individual plates. Sometimes the plates are still in the wrong orientation. And the reason this can happen is that like we have not looked at orientation at all, right? Like the algorithm so far has only been looking at features or joints, hasn't really considered the 3D orientation. So when it's wrong, you can use this rotate icon to override the suggestion of the system and then manually fix that. In this case, it was actually correct. So I kind of undo that transition and continue to assemble this VR headset. And you see the search space for a user is actually not that large, right? Like there's like, it highlights only the joints it can pair up with. So you kind of know where you can go. And because you know what the VR headset looks like in the back of your mind, you can actually kind of successfully assemble this model in a relatively short amount of time. And the best part of this workflow is that it's already in a 3D modeling environment. So right now, all I need to do as a user is take another tool, like for example, the stretch tool, to modify that VR headset in 3D. And now I have a VR headset that is optimized for my use case, for my machine, and for my material. So we've used Assembler Cube to reconstruct 100 models that we found in online repositories. And this is just sort of nice to watch. So I hope the video catches up so you can actually see this. So I'm assembling here like a chair model. And as I go through these different models, you get a bit of a sense of the different types of joints and structures that I'm looking at. Here's a candle holder.
I'm sorry, I think the video is catching up.
There we go. Now it's catching up. Yeah, it was. Now we're on the chair model. It was still showing HMD.
I see.
Yeah. Now
pause it for a moment.
Oh, now the candle holder's going. Yeah, that's good. Yeah. And now you're
yeah.
onto the.
You should
like
already be seeing the next.
A birdhouse now. Or something.
Right.
Yeah. So yeah.
That's right. Yeah. So yeah, that's right. I'll just let it play it and then maybe just give it a moment afterwards where you can all catch up with what you're seeing. So yeah, here's a birdhouse, and you see that sometimes you still need to use this rotate icon to override suggestions of the system. But you get it right like in 1 or 2 clicks most of the time. Here's the microscope, and here is then the Raspberry Pi rack for those people who still want to mine Bitcoin at this point. I would recommend it. Test tube rack, and of course we could also not resist the urge to reconstruct a dinosaur. And 100 other models that we found in these online repositories. And hopefully the video catches up by now. So all of these models at this point, they kind of gained massively in value, right? Like they were shared as 2D cutting plans, and they would only be able to be reproduced on one particular laser cutter in one particular material. Now they can be fabricated on any laser cutter and in a range of materials. And it's possible to make parametric changes to these and continue to modify and increase the complexity of these models. So if you look back at the algorithm, the 5 steps of Assembler Cube that I've shown you before, we've actually achieved relatively high success rates in the first 3 steps of this algorithm. Furthermore, like the first 4 steps of the algorithm actually are also extremely performant. So like in about 107 milliseconds on average for the models that I've shown you before, it would actually be able to compute all of the underlying structures. The obviously weakness of this algorithm is the semi-automatic assembly, right? Like the user needs to come in, understand how the model works, and then kind of reconstruct it and puzzle it together into that 3D model. So in a follow-up paper, we actually tried to address that problem by trying to automate that process, with a software system called AutoAssembler. So AutoAssembler does automatic 3D reconstruction by beam searching the exponential space of combinations of plates using a heuristic function. And the same workflow that I've shown you before now looks like this. So a user again loads the same 2D cutting plan into the editor. But in the background, the 3D modeling environment now starts to kind of explore that exponential space of ways to combine the plates and traverse this until it finds actually kind of correct assembly of this model. And because you're, again, in a 3D modeling environment, you can immediately apply your changes. So you have the 3D model as a user right away. You can just make your changes and continue to kind of do what you actually wanted to do, which is fabricating that particular VR headset. Obviously, the secret here is what happens under the hood again, right? So let's look at the actual algorithm here. So like the algorithm, the beam search algorithm starts with the plate with most joints on it. It then tries to add each of the other plates into the current assembly and assesses these situations with a different scoring function. It picks the best scoring candidates and then recursively repeats that operation until all of the plates are assembled into the model. And there you have your VR headset. And so as we know, beam search worst case complexity is O of D times K, in which D is the depth and K is the beam width multiplied by the maximum fan out. And the maximum fan out in this particular case is actually also dependent on the depth multiplied by the number of available joints in the model. So, you know, the worst case complexity would kind of go cubic in the number of joints in the model. And so like that's not great for models that are higher in complexity. The good news is that the hash table that we have like presented before actually allows us to limit that fan out to only joints that fit to the current candidate, resulting in much better performance, unless all joints in the model are exactly the same, where we have a puzzle. Right, at this point, like the hash doesn't bring us anything. You still have to compare every plate to every joint to every other joint, and the complexity would be very high. It would take a long time to go through all the different states. If you look at that in more like sort of pseudocode, you see that there's this kind of big while loop which is D times executed, right, for each of the plates, trying to kind of go through all the different states. And then the current candidates at every level, they are limited to this beam width factor. The beam width is then multiplied by all candidates that can be created, so this maximum fan out, which again, like worst case, results in quadratic complexity within that while loop that is already executed D times. And therefore, the scoring function has to be extremely efficient, right? If you do anything inefficient in the scoring function, that would be kind of amplified in cubic complexity. So like that would make things really, really bad real quickly. The way we address it is by kind of creating these different heuristics, right? So here's the 6 heuristics that allow us to kind of assess the quality of assembly. And I'm going to go through these heuristics in detail to give you a sense of how they really work. So the first heuristic is to give preference to compact candidates. This magazine holder here gets a really bad score because like this plate is sticking out in an awkward direction. Auto assembler gives a much better score to kind of this configuration of that particular model, where that plate is flipped inwards and therefore the overall bounding box of the model becomes much more compact. And it uses that heuristic to kind of assemble this magazine holder. Auto assembler avoids intersections between plates. This train wagon here, like obviously has this red plate that is intersecting with the other plates in the model. And so it gets a really bad score. It gets a much better score to this configuration of that model, where that plate is flipped outwards and no longer intersecting. And use that heuristic to kind of continue to assemble this train wagon. So these were a little bit obvious, right? Like, I mean, of course you don't want to have intersections, and of course you want to have sort of a reasonably compact model. Let's look at the more kind of ambiguous ones. So the third heuristic is that the auto assembler gives a preference to unambiguous joints. If you look at this plate here, this red plate can be assembled in 12 different ways into the base plate that you see out here. And this gets even worse when the next plate is assembled into that, which is again very ambiguous, right? So the complexity now goes through the roof. Auto assembler gives therefore a bad score to assembling this red plate and a much higher score to assembling this green plate here, which can only be assembled in 2 different ways into the current plate. It uses that to kind of constrain the search space at any given moment in time, so that it now assembles this other plate that can only be assembled in 2 different ways into the plate, which now in turn constrains that red plate that we were looking at before, and use that heuristic to kind of assemble this dice tower model. Auto assembler minimized the number of unmatched joints. So in this desktop organizer you see here, this red plate is actually correctly assembled, but it also adds a lot of different joints here to the model that are currently that are like opening up the search space. Right? Like the more joints you have, the more kind of matches you need to find. So auto assembler gives a bad score to assembling this plate and a much higher score to assembling this green plate here, which actually fills up 2 joints and only opens up 1 new one. And it uses that heuristic to kind of assemble this desktop organizer. Auto-assembler makes use of constraints that are posed by other plates. So here's the VR headset again, and this nose piece here is accidentally correctly assembled right now, but it would, from an algorithmic perspective, just as well be assembled this way or that way. Auto-assembler therefore gives a really bad score to assembling this red plate right now, and a much higher score to assembling this green plate, which is fully constrained by its neighbors. And this in turn now constrains that red plate we were looking at before, and then allows us to kind of assemble this VR headset. Finally, auto-assembler favors symmetric candidates. So this birdhouse that you see here looks like it's correctly assembled. However, this red plate here is flipped the opposite way. Like it's like the joints are on the top, whereas on the other plate, they're on the bottom here. So the next plate will not be able to fit in place. As we are going through all the models that we've been going through, looking at, we've noticed that a lot of models kind of exhibit high degrees of symmetry. So we use that symmetry to kind of inform how plates can be oriented correctly in the model. In this case, the bottom plate, the symmetry of the bottom plate infers that like the red plate currently is misassembled and therefore gets a bad score. The opposite orientation of that plate, where the plate is flipped downwards, gets a much better score, and that allows us to actually kind of correctly assemble this birdhouse. Now we have these 6 different heuristics, and they are like still like sort of all roughly independent of each other, right? So in order to kind of find out how to kind of really combine these together into one consistent scoring function, we use hyperparameter optimization using the 3,000 estimator that was posed by Roumen et al. In 2020. And this converged after feeding around 2,000 synthetic states of these assembled models, giving us like the values that you see over here. So these are the different weights that are associated to each of these different scoring function, these parameters in the scoring function, which then produces one consistent function overall. We were a little surprised by some of these numbers though. Like for example, intersections here, like we had sort of expected that the value for intersections would be 1, right? It's a hard constraint. You never want to have intersections between plates. However, when we like look back into sort of the pseudocode and how this was implemented, we have to remember that this scoring function was like aimed to be as efficient as possible. And so it makes a couple of assumptions that are not quite correct at any given moment in time. For example, in order to calculate like intersections, it uses the object-aligned bounding box of the assembly and compares that to the last plate that was assembled into the model. Obviously, anyone in the room right now is thinking of like 10 different use cases where that may not work out, right? Like where it's a little bit naive to do, but it's very efficient to compute, and combined with the other heuristics still allows us to kind of get to a good assembled state in the end. So this is the reason why like the weight of that, the intersection checking had to be lower, because it has to account for these false positives that are implied by the efficiency of the scoring function itself. Then other things in the overall sort of pseudocode that we had to kind of tune here is like the beam width itself, of course, right? It's a crucial parameter. And so we did that by just experimentally kind of going through like a benchmark that we produced, where we looked at like how the success rate sort of improved as we kind of kept increasing the beam width. At about a beam width of 4, they started to kind of flatten out a little bit, not entirely. So we had like still an increase, like when you go to a beam width of about 14 or 15. But as you see, like the performance also goes up with an increased beam width. So like we decided to cap it down at 4, as the results would already be relatively good, rather than 79% accuracy. And the ones that are still wrong, you can easily override by kind of, after assembling the model, reassembling one of the plates, and then fixing the model as a result. So here you see that algorithm in live action. So you see it assembling a bunch of models in the background. Most of the time, it takes like 1 or 2 seconds per model to kind of assemble them. And the biggest amount of time currently lost is in the rendering of the screenshots. Which is still kind of entertaining for a user to watch, of course. Once you're done with like assembling the model, you have like sort of the 3D model that you see here. You can immediately import it into the environment and start to make the modifications and do the things you want to do with it. All right, so in conclusion, I have shown like how to go from 2D models, the state of the art of 2D cutting plans, towards 3D models. That's sort of the more flexible format that allows you to make all these parametric changes and build on the work of others. This is all to kind of overcome these issues that I've identified with the 2D cutting plans, these 3 different types of issues. And in some ways they propose an alternative way of sharing models by building on the work of others, increasing the complexity, and really kind of leveraging the knowledge of like models that are out there already. And I can only begin to imagine what the type of diverse use cases that can start to emerge from this when this technology truly becomes ubiquitous and many more users are starting to kind of contribute to the models that are out there. So this is sort of my contribution to make a small step towards portability in the context of laser cutting. And like if I look at on any of these other fields of digital content, I get particularly excited about what that future for laser cutting could look like if we really succeeded all the way down to this. When I teach an introduction to kind of computing, I try to convince my students that like compilers was the moment where we went from thousands of users of computing to millions of users of computing. And I hope to have today convince you that maybe to some degree, the transition towards like portable laser cutting would be the moment where we can go from thousands of users of laser cutting towards millions of users of laser cutting. And if you zoom out one step further, there's a bigger picture here somehow, right? Like, so laser cutting is one particular fabrication technique in a bigger scope of like different fabrication machinery. So I think like for the bigger field of fabrication to succeed, we can look beyond just laser cutting itself and see how like the ideas and thoughts of this thesis of this work kind of be applied to the other sort of fabrication techniques that are out there. So 3D models for laser cutting could be one small step in that sort of transition where we go from hardware specific to kind of more machine independent fabrication techniques. But then there's also like other kind of properties you might want to abstract away, right? If we look at like not just the shape, but also the compliance or the weight of the structures, or other sort of mechanical structures that you might want to kind of abstract away and kind of make reliably reproducible across machines. We can look at portability for other machines, right? Like 3D printing, milling, vacuum forming, injection molding. And ideally, I think if this were all to succeed, what we really should start to look at is to start building systems that allow us to model and modify products as opposed to processes. So what I've shown you all so far is all very much focused on laser cutting, right? It's like you make an assumption about the technique that you have, and then that's the result you produce. So you can make a guitar using laser cutting, which is really cool. But what you really want as an end user is a guitar. You don't care about the fact that it's laser cut. It's not interesting. It's only interesting to the people that like some of us are in the room right now who are just really excited about the technology itself. So I think like ultimately, if we really want to succeed at like kind of achieving portability in the context of fabrication, we really need to kind of start creating a more like integrated environment where we use the different machines for the things that they are good at, and avoid like kind of creating a neck for a guitar that is like actually relatively weak using laser cutters, which you could have made using milling in a much more elegant solution. And if you zoom out even further, compilers were like one step in the history of computing, right? But there's much more. Like there's been much more going on in the timeline. There's been the introduction of reusable components, configurators, and later even mobile computing. And there's like many of these sort of pivotal moments are great to look at in the context of computing and sort of trying to imagine what impact they could have on the future of fabrication. Because like thankfully our timeline is like behind a couple of decades behind the sort of introduction of computing. So there's a lot of like kind of ideas that have happened in computing that could be applied to the context of fabrication and laser cutting that I'm very excited to sort of start to investigate with a new team of researchers over here in New York City. Some early explorations, for example, looked at like how to create reusable components in the context of 3D printing, or how to even do mobile 3D printing on the go. So there are some early projects I've done. There's much more of that coming in the upcoming years. So on that note, I would like to thank you for your attention, and I very much look forward to kind of discussing all of these ideas and thoughts with all of you. Thank you.
Amazing work. Thank you. Thank you so much, Thijs. If anyone has any questions, please raise your hand or maybe write them, or even you can just ask the question now. I will start us with one question. Do you think we will have artificial intelligence or machine learning to see all these assemblies, have done multiple of them, and it train itself to figure out the right configuration? Or do you think that will be not necessary using your algorithm that you have at this stage?
Yeah, so that's an interesting question. So like, I think like, so what I've done so far is very much not artificial intelligence, right? It's like sort of like using heuristics and kind of understanding, embedding some of the information we have about laser cut models to kind of like succeed relatively efficiently at like sort of like assembling these models. I think there is something to be said for, there is a case to be made for artificial intelligence here, and it's certainly to be made as there is more content available. Like right now, it's like sort of a bit of a chicken and egg problem that you typically have with AI, right? There's a reasonable amount of laser cut models, but not that many, and they're all very much like handmade at the moment. So like they exhibit a whole really broad range of different patterns that are very hard to sort of extract and really kind of nail down like how they are to be assembled. I do think as a sort of the content of the number of like models sort of goes up, and the models that are being shared go up, this will get better. It will still remain a tricky thing because if you look at what is being shared in online repositories right now in terms of laser cutting, I don't know how you feel about it, but I don't get particularly warm from the content that I see out there. There's a lot of crap, to put it frankly, and that's very unfortunate, because like if you start learning on that crap, you will just kind of get really good at reproducing more of that somehow. And this is a little bit of like a frustration that we have encountered, as that's why we think like this 3D modeling environment is a much more promising direction to kind of go in, because it will kind of make it much more likely that you produce consistent and decent stuff somehow, things that actually work. Whereas like if you just kind of keep hacking around in what is out there right now, I'm a little bit skeptical about what we will really succeed at making in that way. So I think, and this is also a little bit like part of my thesis in a way, is if we continue to do more of what we have been doing in the past, and kind of make it more focused on sort of the makers that are currently using laser cutters, I think we're sort of hitting the wrong nail. Like we'll make progress to make like the current state of the art better, right? Like that's nice. But we all miss sort of this potential to look at what the other 99% of people are interested in and how they could benefit from laser cutting. And that takes a very different way of thinking, I think. So yes, in the very long run, as there's more kind of really high quality content that is being produced and there's more stuff out there, I think like AI is certainly like a good way of doing this. I've personally been looking into computer vision as well as like sort of an alternative way of like sort of reconstructing these models, right? Like imagine that you have a picture of the result and you have the 2D cutting plan. You would actually be able to get much closer to success. Like there's a lot less like sort of guessing that you need to do in order to kind of get to the correct outcome, because you know roughly what you're trying to make. And most of the time it's available, right? Because you don't just download the 2D cutting plan from the web, but you would typically also know what you're trying to make. So the combination of those different types of information might actually kind of get to the point where like AI can play a more central role and actually kind of detect more primitive like patterns in there that would then allow us to kind of like really efficiently kind of reconstruct these models in 3D. So that's certainly like one thing that I see as very, very feasible in the distant future.
Yeah, I agree. I think need to build on something that is good, not difficult to build on or train the AI in a bad way.
Yeah, right. Exactly.
Mark, you have a question?
Oh yes, really nice talk. I'm really impressed with the software tools that you're building. I'm just wondering if you want to have a comment or discuss about what's the role of the open source community in this. So of course, with open source hardware, that helped drive a lot the adoption of 3D printers, and there's a lot of sharing of models and so on. But is the software that you're building is also an opportunity for the open source community to get involved and to create also some software tools for creating printable 3D models and the like?
Yeah, that's a great question, and I wish the answer was yes. As I also mentioned in the middle of my talk, we're currently also in the process of like sort of rolling this out into an actual startup, which we're so for which the source code currently is not open. We do have this public beta that we're running, so there's a lot of people who are currently kind of using our software, but access to the source code is probably not going to happen anytime soon. The main reason for that is like that it's competitive advantage, and we're currently in the process of like really rolling this out as a curriculum in schools. So we're giving a lot of people access to being able to build with the software that we're providing, but like kind of to modify the software itself and to kind of build on that is currently not in sort of the projection where things are going for this at the moment.
But are you aware of any other open source efforts that are doing something similar?
So there is, you might have seen a research project called FlatFab, which is also sort of like doing some sort of 3D models for laser cutting, but they are very much focused on these cross joint structures where you have like these, the typical model that they show is this dinosaur. Like I think I probably have like somewhere a picture of that in my, these type of structures. They are very flat fab sort of S structures. Where so like that their software is open source. It's not supported so much anymore, so like it's still like you can have access to the source code. I still managed to kind of compile and make it work, but it's sort of in its last stage of like being maintainable at the moment. And then there's a lot of very open source projects which are like sort of more just kind of creating enclosures or boxes using laser cutter. So they are like a little bit simpler. They're not these 3D modeling environments, but it's more like parametric modeling tools that allow you to kind of make simple structures using laser cutting, or very specific ones. Like here's one that generates traffic lights in different configurations. So there's a couple of those things out there. I think in the end, I'm like, so I am fully I'm part of that community, right? I also like to kind of hack around in code and like kind of build things from the building bricks that are out there. I think in order to kind of make this really relevant for like the other 99% of users, the open sourceness is not so much the key question right now. I think the reason why we are like rolling it out in educational context right now is that actually kind of is a way to kind of make the technology accessible to many more people in more meaningful ways, as opposed to here is another sort of maker project that gets you halfway there somehow. So I agree. Like if I could now say it was open source, I would be very happy, and I would like hope that you guys are all sort of like building cool features on top of what we already created. But I also have to say that like I think for this to succeed and have bigger impact, maybe the way we're going down right now, or at least Cube is going down, like I'm not part of their team anymore. They are doing it as I think going in a very promising direction. So I hope to see much more impact with this software in the distant future that way.
Great, thanks for that.
Yeah. I was wondering if the assembler or would suggest like for sustainability would suggest places or to reduce waste or reusable component. I know it reads the model and try to find how it fit and assembles, but would it like to say, if you are going to rebuild this, it will suggest maybe an optimal build structure?
That's a very interesting idea. I think like assembler cube or auto assembler could play a role in that. I also think that like one thing that we're actually looking a little bit into right now is like to embed non-laser cut content into the laser cut models, because it would allow you to need already reuse like kind of objects, elements, things that you have out there that would get you to a much more successful state of that model. But I really like the idea of like sort of like making suggestions on how you can kind of be more efficient about the material, how you can be more sustainable and more kind of considerate about what you're making, as opposed to just like, oh, I click together a whole bunch of boxes and I just see what happens. That might be very wasteful if done inefficiently. So like to kind of to emphasize a little what I was trying to say earlier, like so like we're looking when we're building this guitar. Obviously, you could make the whole thing using laser cutting, right? It's probably possible to create like these knobs from laser cut wood, and there is a way to do this. It's just not the best solution out here, right? Like it's like even though like these pieces are not laser cut, these pieces are not laser cut right now, they are still sort of more efficiently fabricated at the moment, and particularly because you can already buy them as off-the-shelf components. So like it's an interesting question of like how you can sort of start embedding other content into your model to enrich the model, to kind of increase what you can do with it, but also at the same time to kind of be more kind of considerate about what you have and what you can reuse out there in the model already. So this thing is actually completely modeled actually in the laser cutting environment. So here you see like the actual kind of model in the editor, where you see is that not only the plates, but also all the other components are sort of part of the same structure and model. It's a good question, yeah.
Nice. I think in the lab we have few of us have tried to do laser cutting, and we have to build prototype here. I was wondering if Tamil or anyone from here has difficulties or experience they would like to see the laser cutting in the future. Maybe it's a good time to ask. But from my observation, we also build EEG, or we use EEG devices to measure the brain, and I was wondering if the structure of, because everyone has different head, and if we can build sort of using laser cutting a structure that can fit different head sizes. And there's a follow-up question about, would it work with flexible material, I guess. I know that doesn't apply to laser cutting, but if, for instance, laser cutting on fabrics, would assembler or cube play part here?
Yeah, that's a good question. So the answer is yes. I think laser cutting would be a great tool to kind of make things that are adjusted to specific human dimensions, or like kind of mountings on arms or in your head or any of these things. One part of that is by kind of making the rigid structure more flexible. So you see that actually a little bit in the guitar shape that you see here, where you kind of add these additional curves to kind of make the material more flexible, and then you can actually bend it around and kind of give it the springiness that it would require here. Another part of that answer is like sort of what I actually did in the beginning of the talk, right? Where you add these additional springs into the mechanisms. The spring is actually, so in some ways, the right answer to this, right? Like in some ways, what you want is not a rigid connection, but you want to have something with a larger tolerance so that it fits to a range of like different head sizes or arm sizes in that sense. So by adding these additional kind of cantilever spring mechanisms inside the structure, you would be able to kind of also accommodate for a much broader range of variations. And to kind of answer the other part of your question, the flexible materials, laser cutting totally works on textiles, on leather, on flexible materials. So yeah, you can absolutely do that. This is also, it actually works really well on that. So like, it's actually really nice results you will get when you're trying this. Whether that will work with assembler cube is yet a completely different type of question. So the thing with assembler cube is, and with the software that I've been writing, is that it makes assumptions about the rigidity of the material, right? If you think about like the search space of like assembling, for example, these two plates with respect to each other that you see here, the search space is tractable for me, is discrete, because I can assemble that plate in 3 different configurations, right? I can do it either flat, I can do it one way up, or I can do it down. That's really nice. That's a really good feature for like what I'm trying to do, like, because I'm trying to kind of reconstruct the structure of this model. But then when you have like completely flexible materials, that is a continuous search space, right? Like, so like now it can be assembled in any kind of angle, in any type of orientation. And that's going to cause severe trouble for like, especially auto assembler to succeed, right? Like auto assembler will just kind of not be able to the search space is no longer tractable. It will just not compute. With assembler cube, we've looked a little bit into this, because often it's like you would still have additional joints, right? Like, so like you would not, if you have only flexible joints, okay, we're done. Then there's nothing we can do. We don't even have a way to represent it in cube right now. But if you have like a few joints that are rigid and a few joints that are flexible, you can actually still manually say like, okay, well, this joint actually goes here. Even though like it seems like intractable from, like a material perspective, it will just allow you to place the plate over there, so you can still create the right structure, and then like kind of later on assemble the flexible material on top of that. So there are ways to manually do this, but automatically flexible materials are pretty much the enemy right now. I'm very interested in ideas. If you have any thoughts of how we could address that, like I think there are ways to do it. There is like, because you will know from how the model is like constructed, whether a plate is going to be flexible or not. So maybe there is a way to sort of use a different type of algorithm whenever we're not dealing with rigid plates, and then you kind of use that logic to sort of solve the problem. But it certainly requires a lot more sort of investigation here, and happy to continue the dialogue offline.
That's great. Yeah, the possibilities are more, I guess, different and diverse for flexible materials.
I have
Yeah.
another question. I'm just wondering about how you would extend your work to also support 3D printing. So obviously you're focusing on laser cutting and tools for helping cutting, but I imagine that some of those tools would also intersect with printing tools, and then you can imagine fabricating objects that were a combination of laser cut and printed components.
Yeah, that's a great question. So like, I mean, I've shown a little bit of like sort of where we're trying to embed like non-laser cut geometry in laser cut structures. So you could imagine that non-laser cut geometry being a 3D printed component that you can embed in the structure. But like the deeper like sort of idea of like portability and like how to kind of make individual parts work with respect to each other is a problem that is not just limited to laser cutting. So like I've tackled it in the context of laser cutting because like this is sort of where I knew I could sort of solve part of it and kind of build some software to support this. I've been looking into this for 3D printing as well. So like there is this, there was this Kai 2018 paper where we looked at how to kind of combine different 3D printed geometry into a new model. So it raises a lot of similar questions, if you will. So like there are like different components, they need to be assembled. There are different pieces of 3D printed geometry. And we want to find a way to kind of put them together into a new model. So you take like the three colors of this centrifuge represent three different source models. So like they're sourced from different models that are found in the wild, so to say. And in order to combine them, you need to think about sort of the interface between the pieces again, right? It's pretty much the same type of questions that I've been trying to solve in the context of laser cutting that I'm solving here in the context of 3D printing. So you have like all these interfaces where you have like, okay, here are two mechanisms, they want to match with respect to each other, but in order for them to match with respect to each other, you can not really change, like, for example, the teeth of the gear or anything. You can only change for example, the axle where they kind of interface with one another, and then recombine everything that kind of comes with that to kind of remix it into like a new type of machine. So that's like a one step in that direction. And I think there's many, many more sort of related sort of questions that are out there when you're trying to kind of combine 3D printed models or kind of try to use different types of 3D printed models and integrate them together. So there's a lot of these sort of the questions that I've been trying to address that continue to apply. And then there is also like a whole bunch of things that are even more specific to 3D printing that would be interesting to investigate as well. Like, for example, you would have a 3D printed model, and rather than like trying to preserve the structure, which is an obvious thing to do because you have it already in 3D, what if you try to kind of preserve another dimension that is like one level higher, right? In laser cutting, we've looked at like, okay, you have plates that are 2D, like how to turn it into a 3D model. In 3D printing, you have a 3D model, so that's fine. How can we kind of preserve other properties? So like, what if you want to kind of create a structure that is equally compliant as a different structure, right? Like, so you want to change the material behavior by varying the structure so that the same 3D printed model would fabricate reliably on a different 3D printer. Because you have exactly the same problems we have with laser cutting, right? I'm not sure how much you've been trying around with 3D printing, but like, the models are sort of like a product of the fabrication process that we have right now. And that involves the materials as well as the 3D printer itself. So you can imagine like you have like a structure, you want to kind of change the compliance, but you use a different material. Can we do that? Can we change the structure so that it actually continues to do the same, perform the same function, even though the 3D model, the underlying 3D model might be changed? And then we're pretty much in the same territory as what we're doing with 2D right now in laser cutting, right? So like on a 2D level, we're abstracting to 3D so that we can actually kind of reliably reproduce the same plates in 3D again. So like the same type of questions apply. And I think there's a lot of like interesting sort of investigations that we can do in this direction in the distant future.
Great, thanks a lot. That was great.
Thank you. I'm guessing there are no more questions remaining, but I appreciate the time that you spend with us to talk about this project. It's very exciting, and it will be good to see this project more used and commercialized, or we can contribute to it as well in the future. Thank you so much for taking the time to talk to us, and we hope to see you here in New Zealand or Australia one day soon.
So do I. Thank you so much for inviting me. It was a great pleasure to talk with you all. And I really liked the discussion and the type of questions that you guys have asked. So it was well worth my time. Thank you so much. And if you ever happen to be in New York City, please swing by.
Yeah.
forward
We'll
to
see you
meet you all
later.
in person.
Yeah, thank you so much.
Bye.
Bye. Bye.
Thank you.